This is a problem. In order to find the correct answer, okay, you need to use a little bit of combine a couple of principles, okay, do a little bit of math. It's not easy to find the correct answer for this one. However, it should be extremely easy. It should be a second thought for you to narrow down the possible answer to only two. So, and if you do that, if you have done that, if anybody has done that, and they say, well, I narrow it down to these two, and just 50-50, I chose this one, I got it wrong, and he came to see me and said, look, professor, okay, no, I can tell you why I narrow it down to this, okay? I give you credit, because then you know, I probably would change my rules and just pretend that you did it right and change your grade and not tell anybody, because that will tell me that you really understand the physics. And I don't want you to solve this problem exactly, I would just, let the engineers work on that. Okay. Let's make, I told you very early in the course, okay, that the fundamental tool to solve problems is to do a motion diagram. Okay, so let's do a motion diagram roughly, okay? So I'm going to do this, okay, here. So, motion diagram has the velocity. Okay, the velocity is always easy to figure out because the velocity is just the direction in which the object is moving. But the reason why the motion diagram is so useful is because it allows you to figure out the acceleration. Okay. How you do that? Well, you just use the fact, okay, that if you have one velocity, okay, you get the next by using the definition of acceleration. So the next velocity is the current velocity plus the acceleration times the time. Okay, so if I call this one 1 and this one 2, let's say, well, what do I need to add to V1 to get V2? Okay, one easy way of doing that is you just take the V2 and you put it with the same tail as V1, and you put it sort of here. This, okay, this will be V2. And now you know that A delta T has to be this. Okay? So what this means is that when the sphere goes to reaches the bottom, at that very bottom, okay, the acceleration is up. Okay? You can tell that because at the bottom, okay, so you're going to have velocity in that direction. Okay? But the nanosecond later, the velocity will be like this, and like this, not like this, okay, and then like this, and like this, and like this, and like this. So your acceleration is changing. The acceleration is whatever changes this vector, okay? And so if you want the vector to do this, okay, you have to push it up. So that's what the acceleration is doing. So this acceleration is pushing. Oops, can't go there. It's pushing this velocity vector up. So the V2 is now pointing up, pointing slightly more up. Okay. You can always tell, remember, if you go back to the notes, okay, whenever you have some sort of motion in a curve, there is always an acceleration towards the inside of the curve. Okay, this is a special case for a circular motion, there is an acceleration. Okay. So now, we know that this is acceleration up, okay, and that's what we learned from the motion diagram. Now we use the second fundamental tool that I told you have to use for all problems. Okay? And that is doing free body diagrams. Okay? So to do a free body diagram, okay, we need to identify the forces that are acting on your object. Okay? Now, in order not to be confused with the centripetal force and the centrifugal force and all these good forces that appear there and the acceleration, complete acceleration forces. So forces are the interactions of your object with the rest of the world. Okay, so here is your sphere. Okay? It's actually here, okay? And you say, well, how is the rest of the world, the rest of the universe interacting with this sphere? Okay? And so the first thing you say, well, is anything touching my sphere? Yeah, there is something touching because it's hanging from a cord, from a string, from a rod, whatever it is. So there is a force there. Okay, what name can we give this force? Tension, for example. Okay? And then, is anything else touching it? Nothing else is touching it. So there are no more contact forces. So the only other possibility is a long-range force. Something that interacts with this thing without touching. Okay? And the only force in this semester that we have of that nature is the weight. Is the gravitational attraction by the Earth. The Earth does not need to touch it in order to attract it. Okay? So we have the long range. Okay? We have the weight. Okay? This is quite stupid, but it's the only way to make sure that you don't include forces that are not forces. Okay? Because you start adding the centrifugal force, the centripetal force, the net force, and you can find a huge number of things that are called forces. Okay? These are not the ones we need here. Okay? So for a free body diagram, we need to include the ones we identify this way. See what is touching your thing, make a list, and then if there is weight, add weight, and that's it. Okay? With that, now we can do the free body diagram. Okay? And so, how many forces do we need to include in the free body diagram? 2. Okay? 2. Okay? Because we have tension and weight. Nothing else. Otherwise, we achieve. Okay? So we put here the tension, and we put here the weight. Now you may wonder, okay, if I want to, maybe I'll be able to figure out how these forces are related, but just for an initial case. So I drew them more or less the same. Is this correct, or should I draw one of them longer than the other? So what do you guess? Will you draw them about the same length? Okay. Okay, so there are people saying, yeah, there are people saying it should be longer. Okay, suppose they are the same. Suppose, well, my first guess is, yeah, the tension is going to compensate the weight. So they should be the same. So suppose that was true. Okay? So now, what Newton's laws tell me is that I need to figure out the net force. So once I have these things, I have to add them up. If these are the same length, if I add them up, what do I get? 0. So F net will be 0. Okay? See that F net is not one of the forces that you include in the free body diagram. F net is the only force you include in the free body diagram is the forces we identify this way. F net is something that Newton tells you to calculate after you get those forces. It's not one more force that you put here. Okay? And what Newton tells you is that the mass, that's the acceleration of the object, better be equal to the net force. So now, if we agree that this is true, this is the law, so you are expelled from this room if you say this is not true unless you do an experiment to show you that it's not true. So if we agree that this is true, and we agree that this is true, we have an acceleration going up, and we agree that this is true, we got a problem. Because here we have net force equal to 0, and here we have an acceleration that is not 0. So mass times acceleration cannot equal to the net force. So there are 3 possibilities. Either Newton's laws are wrong, which are not, okay? Either our acceleration is wrong, or our force is wrong. Now the acceleration, okay, little that could be wrong there. Okay, we figure out from the motion. Okay, there has to be an acceleration pointing up. Okay, so just directly from the motion diagram. So the acceleration has to be right. So what is wrong? So something is wrong here. Okay, the assumption that the tension was the same as the weight is not true. So the tension has to be greater. The tension has to be sort of like this. So that now the net force is like this. If the net force is up, now we agree with Newton, because we have an acceleration up here, and we have a force going up here. The two agree, so we understand the problem. Okay? So, what we know is that the magnitude of T has to be equal to the magnitude of Fg. What is the magnitude of Fg? Just mg, just the weight. Okay? So we know that the magnitude of the tension force has to be greater than the weight. If we go back to the problem here, so we need to look for an answer that is greater than mg. And there are two such answers. 2mg and 3mg. So this, okay, this is something that you should do. And in fact, this is so basic that you should be able to narrow it down if you think that you should pass in the course. Now the rest is kind of the icing on the cake, the difference between a passing and an 8. But you should know this, and notice that you can figure this out without any equation, just getting the basic idea of the pictorial ideas, okay, drawing motion diagrams, drawing free body diagrams. Okay? So and there will be a lot of that in the final exam. So you need to figure out accelerations, you need to figure out forces, and make sure that they agree with the Newton's second law. Okay? So after we narrow it down, okay, now you can say, well, we don't have little time, just guess, okay, we have some time. Okay, it's a 50% probability, it's much higher than winning the lottery. But if you don't have, if you have the time, then you can try to solve the problem, okay? And the way to solve the problem is, let's see. I'll put this on the side here. You see that? Okay? So, I'm going to write sum of forces in the y direction. Okay, so this is going to be the magnitude of the tension minus mg, and that has to be equal, according to Newton's second law, to mass and acceleration in the y direction, and this is mv squared over r. Okay, that's because this is circular motion. Okay, so you know the circular motion, the acceleration, the magnitude of the acceleration is v squared divided by r. Okay, so this tells us that T is equal to mg plus mv squared divided by r. So clearly, the equations are now telling us that T is greater than mg, which is what we knew from the basic diagram. So now the trick is how to figure out what is mv squared. Okay? And so mv squared, where does mv squared appear? In the definition of kinetic energy. So clearly there is this energy problem. You have solved several problems like this. Okay, you have a loop, okay, and you have something making a loop, okay, and you need to figure out the forces, etc. And whether in the roller coaster, whether it will make the loop or not, things like that. And you use energy considerations. So the idea is, okay, that when the mass is here, okay, so if I put my axis here, y is 0, okay, so what would be the potential energy at the bottom? if I put my 0 at that point, the bottom. So this will be 0, okay? So 0 plus 1/2 mv squared, this will be potential plus kinetic. And here, up here, I have mgr, because the height is just the radius when it's horizontal. Okay, and it's coming from rest, so the kinetic is 0. So if I say that kinetic plus potential at the top is equal to kinetic plus potential at the bottom, okay, and you could say, no, that's not really true because there is a tension force, and the tension force could be doing some work. Okay, so what would be the answer to that objection? Say again? Say it louder.
Distance.
Let's see. So I get K final plus U final minus K initial plus U initial, okay, is the work by the other forces that are not including the potential energy. The only force that is including the potential energy is the weight, because this is a potential energy. The potential energy mgy is the potential energy for the weight. But in this problem, there are two forces. Okay, there is the weight and there is the tension. So we cannot say that this is equal to this unless the work done by the tension is 0. How do we know that the work done by the tension is 0?
Tension causes no displacement.
Okay, and it's, yeah, but it does cause some displacement because it does force the object to change the direction it's moving. So somehow it does. But what is the relationship between at any time, the relationship between the tension force and the displacement?
Tension is never in the same direction as displacement?
It's not in the same direction. And how are they exactly related? Because this object is moving in a circle. So if you have the velocity vector, which is the direction of the displacement, and the tension, what is the angle between them? It's 90 degrees exactly, because it's going in a circle. So when the force is at 90 degrees to the displacement, it never does any work. So this force is always perpendicular to the instantaneous displacement. And so the tension force does not work, so we can assume, and that's the same thing you do, say, in a roller coaster, and have the normal force. Okay, the normal force is acting all the time, but you ignore it. You say, well, kinetic plus potential at the top of the roller coaster is even kinetic plus potential at any other point. And you have a normal force that is doing a lot, okay? If you go to a roller coaster, you feel the normal force, okay, doing crazy things on you. But that never does any work because it's always perpendicular to the direction of motion. Okay, so we are safe, we can do that, okay, and then you can say, okay, 1/2 mv squared is equal to mgr. What the need from here is mv squared over r. So mv squared over r is equal to 2 mg. So here T equal mg plus 2 mg. So T is equal to 3. Okay, and this was one of the options, and you know, so it takes a while to find which one is the correct answer. But okay, you can narrow it down to 2. Okay, even if the worst case scenario you have a 50% chance of being right. Okay, so these are